Hello class and welcome back to Unit 2 in Chemistry in the Physical Setting, which is Nuclear Chemistry. And today we're going to talk about natural decay. And our major understanding for today is that the stability of isotopes are based on the ratio of protons and neutrons in the nucleus, that nuclear reactions can be represented by equations, and that each radioisotope has a specific mode and rate of decay. And we'll begin with stability of nuclei. And so the quantities of protons and neutrons in a nucleus determines the stability of that nucleus. And a nucleus is generally stable if the ratio of protons to neutrons is 1 to 1. This is for smaller nuclei. When we get to larger nuclei, this rule changes. But for instance, carbon-12, which is a small nuclei, it has 6 protons in the nucleus. That's why it's carbon. So 1, 2, 3, 4, 5, 6. There's an atomic number of 6. And since it's carbon-12, that means it has 12 total subatomic particles contained within the nucleus. So that means it has 6 neutrons also. So 1, 2, 3, 4, 5, 6. And so the proton to neutron ratio is 1 to 1. And so this nuclei is considered stable and it does not decay. If we were to look at another isotope of carbon, carbon-14, again, since it is carbon, it has 6 protons, but since it's carbon-14, it has 2 more neutrons for a total of 14 subatomic particles contained within its nucleus. And so now the protons are not equal to the number of neutrons. There's 2 extra protons. And so since the ratio of protons to neutrons is no longer 1 to 1, this isotope is considered unstable and undergoes radioactive decay. Another rule is that any element with an atomic number greater than 83 has no stable isotopes. And so if we look at the nucleus of uranium-235, uranium has 92 protons contained within the nucleus, and since it's 235, it has a total of 143 neutrons contained within the nucleus. And so what happens is that since there's so many protons within this nucleus and they all have the same charge, they repel each other, and there's just too many in the nucleus, and so the electrostatic repulsion causes the nucleus to break down. So any element with an atomic number greater than 83 has this similar problem and has no stable isotopes, and every isotope of an element with an atomic number greater than 83 will undergo radioactive decay. Okay, so we're going to focus on only unstable nuclei, which we're going to call radioisotopes. And so an unstable nucleus will decay by emitting a portion of its nucleus in order to become more stable. And so there are a couple different types of decay. The first we'll talk about is alpha decay. And so alpha decay results in the emission of 2 protons and 2 neutrons from the nucleus, which is the equivalent of a helium nucleus. Okay, so if we have uranium-238, it's an extremely large nucleus with over 83 protons, and because of this, it's going to want to become smaller to become more stable. So it's going to lose, and it's going to undergo alpha decay, and so it's going to lose 2 protons and 2 neutrons. And so when this occurs, it then undergoes a process called transmutation, and it changes its elemental identity. Since it lost 2 protons, it is now the element with the atomic number 90, which is thorium. So it becomes thorium-234. Its atomic number decreases by 2, and its mass number decreases by 4. The second type of decay is what we call beta decay. And so beta decay is the emission of a negative component of a neutron. And so what this does is, I know we think of neutrons as having no charge, but in reality they have both positive and negative charge that seem to cancel each other out. And so when the negative component of a neutron is released, then a neutron essentially becomes a proton. And so what this does is for smaller atoms with uneven proton to neutron ratios, this will adjust that proton to neutron ratio to achieve stability. And so looking at carbon-14, as we just discussed, carbon-14 has 2 extra neutrons. So it's not at a 1-to-1 ratio, and it's unstable, so it's considered a radioisotope. But through the emission of a beta particle, carbon-14 will basically have a neutron turn into a proton, which will adjust its neutron to proton ratio. So now it has 7 protons and 7 neutrons. Now, since it has one more proton, is now no longer carbon-14. It is now nitrogen-14 with atomic number 7. So this is, again, transmutation. The nuclei of an atom changing into a nuclei of a different element. And so beta decay, again, is the emission of the negative component of a neutron, which would turn a neutron into a proton. And again, neutrons are neutral, but since the negative component of the neutron is emitted, only the positive component is left, so the neutron becomes a proton. And the last type of decay we are going to discuss today is positron decay, which is the emission of a positive component of a proton. And so if we look at an example like beryllium-7, so beryllium-7 nucleus, again, we have an uneven proton to neutron ratio. We have 3 neutrons and 4 protons. And so this nuclei is unstable. So it's considered a radioisotope, and it's going to undergo decay to adjust its nucleus to become more stable. And so through the emission of a positron, which is very similar to a beta particle, except that it is positive and not negative. So it's the positive component of a neutron. And so what this will do is it will convert a neutron into a proton. And so now we have a nucleus with 3 protons and 4 neutrons. And so the nucleus has adjusted to become more stable. But now again, we've changed the atomic number, or the number of protons in the nucleus from 4 to 3. So now the identity of this nuclei has changed from beryllium-7 to lithium-7. So again, this is just the atomic number, but if you notice for both beta decay and positron decay, the mass number stays the same. So it goes from carbon-14 to nitrogen-14. The quantity of subatomic particles contained within the nucleus does not change. Only the identity of those subatomic particles contained within the nucleus. So we can represent transmutation with nuclear equations. And we do that by representing these transmutation reactions with the symbols of the elements, the atomic numbers, and their mass numbers for both the nuclei and the nuclear emissions. So looking at a nuclear emission, so here we're looking at, again, carbon-14 losing a beta particle and becoming nitrogen-14. And so the atomic number is increasing by 1 and the mass number is staying the same. And so this nuclear equation represents the exact same process. So the atomic number of carbon is 6, so we have 6 protons, and the mass number is 14, so which means we have 14 subatomic particles contained within the nuclei. So 6 protons and 8 neutrons. And so this is unstable because it has an unequal proton to neutron ratio, and so it undergoes radioactive decay, and in this example it is beta decay. So a beta particle is emitted from the nucleus, and we represent that in the equation through an arrow that represents this beta particle now leaving the carbon-14 nucleus. And when that happens, the nucleus then is transmutated into nitrogen-14, now with an atomic number of 7, so it has 7 protons and a mass number of 14, so 7 neutrons. And since the proton to neutron ratio here is 1:1, we consider this nuclei stable, and it will no longer undergo radioactive decay. So these processes follow the law of conservation of mass and charge, which basically means that the mass and charge cannot be created or destroyed. And so the sum of the atomic numbers must be equal on both sides of the equation, as well as the sums of the mass numbers on both sides must be equal on both sides of the equation. So if we're looking at this equation again, and we analyze just the mass numbers, so these top numbers here, we can treat this arrow as an equal sign and see if mathematically the mass on this side of the arrow is equal to the mass on this side. And so if we look at the mass numbers and set this up as an algebraic expression where the arrow now becomes an equal sign, we have 14 equals 0 plus 14. And this makes sense. 14 plus 0 equals 14. And so mass is conserved. We did not create or destroy any mass. The mass on this side, the reactant side of the equation, is equal to the mass on the product side of the equation. And so now we can also analyze the atomic numbers on the bottom and see if we have also conserved mass and charge. So on the reactant side, we have an atomic number equal to 6. And on the product side, we have an atomic number of 7 for nitrogen 14 and -1 for a beta particle. And so if we set this up as an algebraic expression, we get 6 equals -1 plus 7. And so if we look at this, 7 plus -1, or 7 minus 1, equals 6. So that algebraically does make sense. And so the charge has been conserved. The amount of positive charge on the reactant side of the equation is also equal to the amount of positive charge on the product side of the equation. And so we can solve for any unknown in one of these equations simply by applying these algebraic expressions and solving for x. Okay, so the decay of an unstable nuclei happens at a constant rate. And so radioisotopes decay at a constant rate, and we call this half-life. So half-life is the time required for half of a sample of a radioisotope to spontaneously decay. And it doesn't matter how much of the sample you have, the rate is always going to be the same. And that's also regardless of pressure or temperature too. The nuclei decay at a constant rate, and the time it takes for half of the sample to have decayed is what you call the half-life. And so half-lives for selected radioisotopes are listed in Table N of the New York State reference tables. When trying to figure out the half-life of a particular radioisotope, we simply just have to look in Table N. If that radioisotope is not supplied in Table N, then it would have to be given to you in order for you to complete any sort of half-life problem. So let's look at a sample here. We have a radioisotope and we have 32 atoms of that radioisotope. So after the first half-life, half of these atoms will have transmutated or decayed into a different element, and usually a more stable nuclei. So after the first half-life now, we have 16 that are 16 radioisotopes, 16 nuclei that are still unstable, are still radioisotopes, but now we have half of them have been transmutated into a more stable radioisotope. And so again, there will be some time elapse. It'll always be the same amount of time. And so again, after we'll reach a second half-life, and at that point, half of the remaining radioisotopes will have again decayed into a new nuclei, a more stable nuclei. So now, since we have 16 radioisotope nuclei, half of those will decay, which would be 8. And so now we are left with only 8 nuclei or radioisotopes or unstable nuclei. And so again, the same amount of time will elapse. And at this point, again, half now of the remaining radioisotopes will again decay. So since there are 8 radioisotopes remaining, half of them will decay, which will be 4. And so we should have 4 remaining by half-life 3. Okay, and we can continue this. Okay, so let's look at a problem where we can apply the concept of half-life. So here's an example problem. The radioisotope zinc-71 has a half-life of 2.4 minutes. And so the question is, how much of the original 100-gram sample will remain after 7.2 minutes? So the first step here is that we have to determine the amount of half-lives that have occurred. And so the way we can do that is by taking the total time that has occurred and divide that by the length of a half-life. And again, we can find the length of a half-life by looking in table N. Okay, or it will be given to you in a problem. So for instance, it is the half-life of zinc-71 has been given to us. So it is given right here where it says it has a half-life of 2.4 minutes. Okay, so there's our half-life. And so by doing this, so by taking 7.2 minutes, which is the total time that has elapsed, and dividing that by 2.4 minutes, we should get the number of half-lives. And so 7.2 minutes divided by 2.4 minutes will equal 3, so that means we have 3 half-lives have occurred. And so what that tells us is that the sample has basically decreased in quantity by a half 3 times. Okay, so our next step is then to determine the fraction remaining of the radioisotope. So how much radioisotope is left after these 3 half-lives have occurred. And so to do that, we basically just take 1, which 1 represents the whole, and we multiply that by a half for every number of half-lives that have occurred. And that should give us the fraction remaining. So since we have 3 half-lives, we're going to multiply 1 by a half 3 times. So 1 times a half times a half times a half. And what we should end up with is 1/8 or 0.125 as the fraction remaining. So this is the representation of 1/8 in decimal form. Okay, and so now we can apply the fraction remaining to determine the mass of sample left after the 7.2 minutes. So if we multiply the original mass by the fraction remaining, we will then be able to calculate the mass of the remaining radioisotope. And so this equation is represented by the original mass times the fraction remaining, and then that will equal the mass remaining. And so 100 times 0.125, okay, or 100 divided by 8 will equal 12.5 grams. And so that is the amount of the original sample that is remaining after 7.2 minutes. And so these 3 setups, these 3 equations will help you determine either the fraction remaining or the amount of time that has elapsed. So you might have to apply them in different order, but again, if you need to figure out the number of half-lives, it's the total time divided by the length of half-life. To determine the fraction remaining, you simply multiply it by a half for every number of half-lives. So here, since we had 3 half-lives, we multiplied by a half 3 times. And then to figure out the original, the mass remaining, you simply just multiply the original mass by the fraction remaining. And so that is the end of this lesson. And so I hope to see you in class, and have a good day.